In today's video, I want to show you how to design a rotor and XROTOR in just a few minutes. XROTOR is a program for the design and analysis of ducted and free-tip propellers and windmills. It uses lifting line methods under the hood. The best part about it is that it's free, and aerospace engineers know that cost is the most important metric in any project, since the government ultimately pays for it. To get started, enter the aerodynamics menu by typing aero. Next, I like to write out a test text file that I can edit with my own airfoil data. Take the temporary text file and edit it with whatever data you want. It's important to remember that capturing the airfoil aerodynamics correctly is going to be crucial to getting the correct rotor design. To find the airfoil data, you can use another free web software such as XFoil to calculate the polar data, or you can use an online database such as Airfoil Tools or Airfolio to look up the data. After recording your airfoil settings, you can read them back in XROTOR using the read command. Now you can design your rotor by entering the design mode. Here you can also input the design point parameters. For this design, I'm going to use the rotor referenced in Design of Optimum Propellers by Adkins. I'll leave a link in the description below. The hub displacement radius is how far from the hub to start the wake. This is useful in case your blade doesn't start right at the hub. And instead of specifying thrust for this design, I'm going to specify power. Now hit enter and the optimization will run. If you're curious to learn more about this optimization, refer to the Adkins paper, which is similar but not exactly what's used in XROTOR. If your solution converges, you should have a nice rotor blade designed. Whoops, looks like I forgot to turn on the potential formulation. This is a more accurate wake model. You can read more about it in the documentation. And if you rerun the analysis, you get the final rotor design. Now we're ready to compare the results versus the Adkins propeller. Now obviously there's some differences, and please note the difference in units used, but this is not bad for our first try. Now we need our propulsion curves. These are thrust versus power versus RPM curves. To generate them, enter the operation mode and type rseek, followed by the starting RPM, the end RPM, and the step size between each. Type A to hold the blade angle constant. You should now see the following plots, which show thrust coefficient, power coefficient, and efficiency with RPM. The craziness happening below 1200 RPM is due to blade stall and the physics begin to break down, so you can't trust the model there. And now that you're an expert propeller and rotor designer, you're ready to take things for a spin. So go ahead and download XROTOR to get started. If you like this video, please like and subscribe so I can continue generating more content. Drop me a comment below to let me know what kind of content you'd like to see next.